My background is in theoretical cryptography, and I'm now working at a company called Snips, a French startup company, where the basic motivation is to make technology so smart that it kind of disappears into the background. So this means heavy use of artificial intelligence, machine learning, which of course leads to some privacy issues. Because of that, there's been a policy that everything has to be privacy by design. And the approach so far has been to do machine learning locally on the device, so on your phone, because that trivially implies privacy guarantees. But of course, there are some features that inherently require some kind of communication. And for these features, in order to implement them, we can look at some of these more modern cryptographic primitives to achieve that. Okay, so specifically, crypto in recent years has evolved on one field called homomorphic encryption, where we actually do the computation directly on ciphertext. So I can encrypt with my public key. I can send you the ciphertext. You can somehow manipulate the plain text inside the ciphertext, send me back the encryption. I can decrypt and see the result. And specifically, the evolution in this, or the progress in this, has been in developing more schemes that allows for a larger class of functions to be computed. There's been another development as well. It's been around since the 80s, but it's become more practical in recent years. It's called secure multi-party computation, where the basic idea is that we have a set of players, P1 to Pn, that securely wants to compute a function f on their combined input, right? So player 1 has x1 and so on. And now together they want to compute a function revealing some y1 to yn, which is distributed to the players. Traditionally, the way to look at this would be to say, okay, we can have some trusted third party. We all send our inputs to the guy in secrecy. He's going to evaluate the function and then send back the output to each one of us. But then the purpose of secure multi-party computation is to eliminate this third guy and do it directly. And the evolution here has been on practical protocols. So anyways, I just wanted to show a few simple ideas for how to use this stuff to do what I think is kind of interesting stuff. The first thing is it's private location equality. So basically we have two players. In this case, Bob wants to know whether Alice is in a specific location or not. This could be, for instance, is Alice at work or is she at home? But we don't want that Bob learns more than the bit of this. We don't want that he can see where Alice actually is unless she's at home or at work. On the other hand, we don't require Alice to be online. Maybe she's in the metro, maybe there's no connection. Maybe she chose to turn off her phone. And lastly, we don't want outsiders, including us as a company, to learn anything about this at all. In fact, we're going to learn a bit. We're going to learn that communication took place, but we don't want to see any of the locations or anything like this. So the basic scheme for this is that we have Alice on the left, we have Bob on the right, and they could do this directly between them, right? But since we had this requirement of being offline, what we do is Alice knows the public key of Bob, so she takes her location, LA, encrypts it under Bob's public key, puts it up to the server, which is basically a bulletin board that's able to perform a simple computation. And she can do this whenever she wants to. So whenever she arrives home, whenever she arrives at the office or whatever. Then Bob, when he's interested in saying, okay, is Alice now at work or is she at home? He sends the location he's interested in. So LB encrypts it again under his public key. Then the server can do, using the homomorphic properties, a simple computation where it computes a bit that's basically saying, okay, if the distance between the two locations is below a certain threshold, then it's true. Otherwise, if it's not, then it's false. She sends this bit back to Bob, who can then decrypt using his private key. And he just obtained this one bit. Notice here that the server doesn't learn anything because it's just seeing ciphertext all the time. So how can we implement this? What kind of scheme do we need? And the typical one for this is called partial homomorphic encryption. So equality by location is here by a geohash. Okay, so we say that the distance is small if they hash to the same geolocation. Then we need the homomorphic encryption scheme where we have addition, so we can take two ciphertexts. Notice it's not XOR here; it's an operation in the ciphertext domain. So we can add two ciphertexts, and that gives us another ciphertext, with the plain text being the addition of the two. And we can also multiply with the constant from the outside that's not encrypted. Okay. And then our equality is just to say, okay, we can subtract the two ciphertexts. That gives us the difference between the two. If they're the same, we're good. We get 0, meaning that they're actually in the same location. However, if they're not the same, then we get a number. Basically, we get the difference between the two, which is revealing a bit too much. So what we can do is we can mask this by multiplying with a random value. And then this is what the server sends back. So why is this not revealing more than the bit? Well, the thing is, if you get a 0, you get a 0 in the real protocol as well. And if you get a random value, well, if you got the 1, you could generate this random value by yourself, right? You could just think of a random number, multiply it by 1, and so you're not learning anything more than you could otherwise. So that's the first little demo. The other one is, okay, so what if you actually want to know how far he is from a specific point? Here again, we don't want to know the exact location. We just want to see, okay, he's 5 minutes away, but not where he is. So Bob again should learn he should learn the distance. Alice is not required to be online, and again, outsiders should learn as little as possible. The scheme looks more or less the same. The only difference is that now the computation the server has to do is slightly different. For this, we need a somewhat homomorphic encryption scheme, where instead of a distance being determined by the geohash, it's now the typical Euclidean distance. We need again the homomorphic encryption scheme, but now we need that it's also capable of what's called bounded multiplication, where we can actually multiply two ciphertexts and get the result in the plaintext domain. But it's bounded in the sense that there's only a limited amount of multiplications we can do. At some point, the way they work is that every time you do multiplication on ciphertext, you add a bit of noise to the plaintext. And at some point, this noise becomes too much, and you can't reliably recover the plaintext if you know the secret key. But you can do a few, and in this case, we just need to do one, basically. So it's definitely okay. And then the distance is just, if we rewrite the Euclidean distance a bit, we can just compute it like you would in high school arithmetic. Okay. So this was for homomorphic encryption. Well, I guess I should say one thing here. So now we had partial homomorphic encryption, we had somewhat homomorphic encryption, and then the breakthrough that came a few years ago was what we call fully homomorphic encryption, where you can actually run any arbitrary circuit on this. So you can do an arbitrary number of multiplications and additions, and this represents any function, right? Today it's not practical, but people are working on that. Okay, so turning to multi-party computation, taking the server out of the picture, we want Alice and Bob, in this specific case, to know how many contacts they have in common. One bigger use case for this has been pharmaceutical companies that want to see if they've done kind of the same research. They don't want to share research the other party hasn't done, but they would like to collaborate on the results they actually found. Okay, so Alice and Bob in this case want to find the common contacts. It could also be they want to plan in the calendar, so they want to compare what free schedules they have in their calendar. And again, outsiders should learn as little as possible. So I'm actually not going to show the protocol for this because I wanted to do it quick. 5 minutes, okay. So yeah, so just to illustrate the problem here, the setup. So Alice knows a set of inputs, A, B, and C. Bob knows C and D, and then they will run a protocol together, and the output to Alice should be C and the same to B. But no one else knows anything. There's a simple protocol for doing this. I guess if we have a minute, I can kind of sketch it. It's based on the Diffie-Hellman hardness assumption, where Alice will send basically a simple hash value raised to a certain exponent for the Diffie-Hellman scheme to Bob. Bob can do the same. Then they use that Diffie-Hellman is commutative for this. And in the end, they end up with the same value that they can compare. Okay, but that was actually it. Thank you for your attention.